We begin by answering the question, what are neural networks? After completing this chapter, you will be able to describe the differences between machine learning and neural networks, understand how biological networks lay the foundation for artificial neural networks, and describe the single layer perceptron. In order to answer the question, what are neural networks, we need to define machine learning. We begin with an example. One question that machine learning can help with is predicting some type of outcome. For example, you are studying for a certification exam. You ask yourself, if I study really, really hard, and if I put some serious study hours, can I improve my score on my certification exam? This is a prediction problem that can be solved using machine learning. You want to know if your future exam score can be predicted based upon the number of hours you study. This image shows a graph of hours of study on the x-axis versus test scores on the y-axis. Let's assume this data represents prior test takers who were surveyed about the number of hours they studied. Test takers who studied between 5 and 10 hours received test scores between 50 and 60 and failed their certification exam. Test takers who studied between 30 and 35 hours received test scores close to 90 and passed the certification exam. So, yes, it appears you can improve your test scores based on this pattern, meaning there is a positive relationship between hours of study and test scores. Machine learning uses data to detect various patterns in any data set by analyzing and outputting a prediction. The machine learns from past data and improves it automatically. For example, a machine learning mathematical formula or model takes the input data, the table shown here, and learns the relationship between the number of study hours and test scores. In machine learning speak, we try to map the relationship between input data and output data in such a way that it can generalized or be applied well on unseen data. For example, exam day 1 is our original input data. Exam day 2 and 3 are the unseen data. Our machine learning model will be able to apply the learned relationships to this unseen data. Based on our machine learning these relationships, your future test score could be predicted. In fact, the more data you feed it, the more its learning improves. Training of the model takes place by comparing the actual output with the predicted output. A cost function is used to reduce the total error between the actual and predicted values. We will learn more about cost functions in later videos. At a higher level, machine learning is the branch of artificial intelligence, or AI, which is devoted to making machines think and act like humans. In our certification exam use case, our exam machine would have the ability to automatically learn and improve from experience if we'd actually used an ML framework to test the model. The primary aim is to allow the computer to learn automatically without human involvement or assistance and then adjust actions accordingly. A subset of machine learning is called deep learning, which is based on artificial neural networks, which are based on biological neural networks. Let's take a look at that next. In this video, we'll provide a high-level overview of biological neural networks as they are the basis for the creation of artificial neural networks. In the human brain, we have a biological neural network made of approximately 100 billion neurons, which are simply nerve cells. Neurons communicate through electrochemical signals and are connected through junctions known as synapses. When you stand up, walk to your front door, and open it to go outside for a walk, or when you are playing a video game, each of your activities fires up a certain set of neurons in your brain. Neurons also have their own activities. Each neuron receives thousands of connections with other neurons, constantly receiving incoming signals to reach the cell body. Based on the level of information or signals it receives, it either fires up or activates or doesn't trigger at all. Interneurons are the most numerous class of neurons and are involved in processing information. Interneurons in your brain would allow you to draw the conclusion that a red-hot electric stove would not be a good idea to touch. If you need, you would retain that information for future reference and hopefully not do it again. Interneurons are nerve circuits, meaning two or more neurons working together to create a specific response. Interneurons are primarily found in the brain and spinal cord, and they carry the information that allows us to think, act, learn, and feel. Think of a neuron as a tree with roots, a trunk, and branches. The roots or dendrites receive information. Information then passes through the base of the trunk or cell body. Information is processed. Processed information is sent up the trunk or axon, which distributes the new information through the branches or axon terminals, which releases the new information as falling leaves or neurotransmitters out to other neurons. An artificial neuron is a mathematical function where each neuron takes inputs, weights them separately, sums them up, and passes the sum through a nonlinear function to produce output. When we say nonlinear, think of its opposite, which is linear or a straight line. So nonlinear will not be a straight line through a set of data points. Here is an example of a linear model where we have the number of personnel versus employee cost, and a nonlinear model, which is population growth over time. All neurons have three basic functions: receive signals or information, integrate incoming signals to determine whether or not the information should be passed along, and communicate signals to target cells, which are other neurons or muscles or glands. The artificial neuron has the following characteristics. One or more inputs are separately weighted. Inputs are summed and passed through a nonlinear function to produce output. Every neuron holds an internal state called an activation signal. Each connection link carries information about the input signal. Every neuron is connected to another neuron via a connection link. Let's take a look at the single-layer perceptron in the next video to understand how artificial neurons lay the foundation for artificial neural networks. Let's look at a high-level overview of single-layer perceptrons. A single-layer perceptron is a type of neuron having multiple inputs and one output. Input nodes are connected to a node in the next layer. The node in the next layer takes the weighted sum of all its inputs. It is called a single layer because it has one layer that contains one computational node. A computational node is just a place where computation happens, similar to a neuron in the human brain, which fires when it encounters sufficient information signals. Shown here is our certification exam question, this time with an additional variable, hours of sleep. Here, the artificial neuron accepts input data, the hours of sleep and the hours of study, and passes the data on to another artificial neuron. Here we have replaced our hours of sleep and hours of study with the features X1 and X2. Our X1 and X2 input data are fed forward into the input node, which then feeds forward the data into the perceptron's computational node. W1 and W2 represent the weights or how strong the signals are for X1 and X2. So a perceptron consists of 4 parts. One input layer, made of input neurons that take the initial data into the system for further processing. Weights. If the weight from node 1 is stronger than the weight from node 2, then node 1 has more influence on the output. And bias, which is an additional parameter whose job is to modify the output along with the weighted sum of the input to the other neuron. And net sum, which calculates the total sum, and the activation function. The activation function, also called the transfer function, calculates a weighted sum of hours of sleep and hours of study and their weights, and adds a bias with it to output a result. Let's look more into how a neuron processes its inputs. Neuron weights can be adjusted individually as it learns based on actual versus predicted output. The modified input signals are then summed up to a single value. This is where the bias is added. Note, all the neurons have random weights and random biases at the start. The next step is activation, where the result of the neuron's calculation is turned into an output signal. Let's summarize. The single-layer perceptron model is one of the simplest artificial neural networks. It consists of a feed-forward process and includes an activation function inside the model. A single-layer perceptron can learn only linearly separable patterns, meaning it can only analyze the linearly separable objects with binary outcomes, meaning 0 or 1, for example. The multi-layered perceptron model is similar to a single-layer perceptron model, but has more hidden layers. In the next video, we'll introduce the multi-layer perceptron. We begin by answering the question, what are the key components in neural networks? After completing this chapter, you will be able to describe what a multi-layer perceptron is, understand how neural network layers work, describe activation functions, and understand how neural networks learn. A multi-layer perceptron, or MLP, consists of at least 3 layers of neurons, or nodes: an input layer, a hidden layer, and an output layer. Data is fed forward into the input layer. This image shows one hidden layer. That is the layer in the middle. This basic structure is referred to as a shallow neural network. This image shows 3 hidden layers. This more advanced structure is referred to as a deep neural network because it has more hidden layers. Except for the input nodes, each node is a neuron that uses a nonlinear activation function. You will learn more about activation functions in a later video. What if you had to build an ML application to predict the selling price of a house in Boston, Massachusetts, a city in the United States? The Boston housing data set is large and complex and contains a large number of features. As a matter of fact, it contains several nonlinear relationships. What distinguishes single-layer perceptrons from multiple-layer perceptrons is that MLPs can learn both linear functions and can also learn nonlinear functions and can be used for both regression and classification problems. For example, this is a typical use case for a multi-layer perceptron. If you wanted to predict the selling price of a house, that would be a regression problem. If you wanted to classify the houses on whether or not they had a garage, that would be a classification problem. MLPs also do not require your data to be labeled, while SLPs do. This is because a single-layer perceptron is a supervised learning algorithm, which means that it needs to be trained on data that has already been classified. The labels tell the perceptron what the correct output should be for each input. Without labeled data, the perceptron would not know how to classify new data. It would simply output random values. The multilayer perceptron, which is a type of neural network, can learn the characteristics of the data without labeling. You input the data set, and the neural network learns its patterns, learning how to represent the data with features they extract on their own. So let's summarize some of the characteristics of a multilayer perceptron. It is a feed-forward neural network, and this means that the information flows in a single direction from the input layer to the output layer. It has multiple layers of perceptrons. This allows the MLP to learn more complex relationships between the input and output variables. The perceptrons in each layer are connected to the perceptrons in the next layer. This allows the MLP to learn the dependencies between the input variables. The output of each perceptron is used as the input to the next perceptron. This allows the MLP to learn the relationships between the input and output variables. In this video, you learn about neural network layers, which allow neural networks to solve complex nonlinear problems. This image shows an input layer, hidden layer, and output layer. The middle layer is always referred to as hidden, as it hides between the input and output layers. The layers are composed of nodes stacked on top of each other and are connected input to output until the final output node. Signals go from an input layer to additional layers. Each layer is fully connected to the other. There are no loops. This is what it means when you see the term fully connected. You feed your data or features into the first layer because it is used to provide the input data or features to the network. Thus, it is referred to as the input layer. The input layer is the very beginning of the workflow for the artificial neural network. The input layer is considered passive because it does not take in information from the previous layer. No computation is performed in any of the input nodes. They just pass on the information to the hidden nodes. The hidden layer is located between the input and output layer. Hidden layers perform computations and transfer information from the input nodes to the output nodes. A feed-forward network will only have a single input layer and a single output layer, but you can increase the number of hidden layers as much as you want to address data and/or use case complexity. In the hidden layer, neurons or nodes take in a set of weighted inputs and produce an output through an activation function. You'll learn more about activation functions in the next video. While you feed your input data into the input layer, you take the output from the output layers. This is the layer which gives you predictions. The output nodes, yes, there can be more than one, are collectively referred to as the output layer and are responsible for computations and transferring information from the network to you. Since the output layer node may be designed differently according to the use case, let's dive a bit deeper into the network to understand how transformation and activation functions work to solve problems. In this video, let's build on your knowledge of neural network components and learn how transfer and activation functions work. A traditional artificial neuron is composed of some weighted inputs. A transfer or transformation, which is any function that takes the weighted sum of the inputs to a neuron and produces an output value. And an activation function, which is a special type of transfer function that introduces nonlinearity into the neural network. Although the images show two distinct steps, the transfer and activation functions occur inside one computational node. Let's add two features from our housing dataset to understand the mathematical calculations that occur inside a computational node. This image shows two features: house zip code and ocean proximity. Which do you think has more influence on the predicted price? This network takes numerical inputs x1 and x2 and has weights w1 and w2 associated with those inputs. The numerical and weight inputs are summed together, thus the summation symbol in step 1. Additionally, there is another input 1 with weight b called the bias. The bias can be defined as the constant value which is added to the product or multiplication of features and weights. It is used to offset the result. It helps the model to shift the activation function towards the positive or negative side. Step 2 is the activation function. After the numerical and weight inputs are summed together, the node then applies a function f to the weighted sum of its inputs. The function f is nonlinear, and its purpose is to introduce nonlinearity into the output of the node. Since most real-world data is nonlinear, you want to make sure that the nodes learn these nonlinear representations. Note that the node learns both linear or nonlinear decision boundaries based on the activation function. There are different types of activation functions. These three are the most widely used. The ReLU function is a nonlinear function that has a linear shape for positive inputs and a zero output for negative inputs. It is a popular choice for neural networks because it is computationally efficient and easy to train. The sigmoid function is a nonlinear function that has a sigmoid shape. It's often used in neural networks because it can produce outputs that are between 0 and 1. The tan function is similar to the sigmoid function, but it has a range of -1 to 1. And this makes it a good choice for neural networks that need to output values in this range. Take a moment and think about the activation function shown in this image. What type is it? In this video, let's learn how neural networks actually learn the data characteristics and patterns. This image is what we'll use to understand how neural networks learn. Our use case is how to predict the price of a house. Is this a classification problem or a regression problem? If you answered regression problem, then you are correct. You are not looking to classify house prices in buckets of low, medium, or high, but to predict the house price based on a set of features. Now, back to our image. First, let's refer to the transfer function as weighted sum for easier understanding. And let's add y hat as the output. This is commonly referred to as the predicted value. In learning, the predicted value is compared to the actual value. For your dataset, this would be the predicted price of the house compared to the actual price of the house in the dataset. And we've added the summation and activation function formula to remind you of the mathematical calculations. To simplify the formula, let's use notation for the summation and activation function. So, how does a neural network learn? One method is by using the backpropagation algorithm. This image shows the regression problem as a supervised learning use case. The actual values of the size and price of the house are shown in a table and plotted on a graph. The line shown on the graph is the line of best fit and are the predicted values. First, your housing dataset training samples are passed through the network, and the number of training examples in one forward pass is called the batch size. This image shows the output, or y hat, obtained from the network's forward pass compared to the actual output. The goal is to minimize the error, or the difference between the actual and the predicted value. This image shows the error calculations for each individual data point. The error is used to adjust or change weights of the nodes such that the error, meaning the distance between the true or actual value and predicted value, decreases gradually. Why is this important? We need a way to evaluate our predictive model. In our regression housing example, we use the root mean squared error as our cost or loss function shown here. So what we mean by learning is which weights and bias minimize a certain cost function. In our case, root mean squared error. The process for calculating root mean squared error, our loss function evaluation metric, is to 1. Get the errors for the training examples. 2. Compute the squares of the error values. 3. Compute the mean of the squared error values. And 4. Take a square root of the mean. The notation here is to use a little hat symbol on top of the y that represents your model's prediction, and to use a plain y to represent the label. So now, back to backpropagation. No pun intended. Think of our goal as decreasing the distance to the line between our true and predicted values. The backpropagation step is also known as updating the weights, which is a bit easier to visualize. So how is this weight adjustment done? Well, the backpropagation algorithm iteratively passes batches of data through the network, updating the weights so that the error is decreased. In the forward pass, the signal flow moves from the input layer through the hidden layers to the output layer, and the decision of the output layer is measured against the ground truth or actual label. In the backward pass, using backpropagation and calculus, the various weights and biases are backpropagated through the network, making those adjustments. The network keeps playing this back and forth like a game of tennis until the error can go no lower. This state is known as convergence. In previous videos, we've defined neural networks and looked at their components and how neural networks learn patterns in data. We specifically looked at multilayer perceptrons. In this video, we'll look at 3 additional neural network types. After completing this introductory video, you will be able to describe convolutional neural networks, commonly referred to as CNNs, describe recurrent neural networks, commonly referred to as RNNs, and transformer neural networks. There are many other types of neural networks, but they are out of scope for our course. Let's begin by describing use cases for convolutional neural networks. Image classification. Object detection, like in self-driving cars. Or determining if a person is smiling or not. These are all examples of use cases that use convolutional neural networks. CNNs have other use cases as well, such as processing natural language and other complex image classification problems. In an earlier video, you learned about the feed-forward neural network, also known as multilayer perceptron, where you have a series of fully connected layers. But this type of network is not suitable for the use cases previously mentioned. And why is that? A digital image is an array of pixels, and each pixel is characterized by its XY coordinates and its value. Shown here as discrete points on a rectangular grid is a digital representation of a 2D image on the left and a 3D image on the right. Machines view images as 2D arrays of numbers to decipher them. If we include colors, then it becomes a 3D array. To a computer, an image is just another array of numbers. Each object has its pattern, and that is what the computer will use to identify an object in an image. The machine takes this image as input and provides a classification output, similar to the processes followed by the human brain. Is it a 1 or not? In this image, notice that just to capture the rows requires 4 inputs into the 4 nodes for just the number 1. What if the machine had to recognize an 8 or determine if the color image of a dog was a dog or a cat? Images represent a large input for a neural network. They can have hundreds of thousands of pixels and up to 3 color channels. In a classic fully connected network, this requires a huge number of connections and network parameters. So the classic neural network architecture is inefficient for computer vision tasks. This is where the feed-forward convolutional neural network architecture comes into play. CNNs take a regular image as input and provides a classification output similar to the processes followed by the human brain. This image shows a CNN predicting cat as an output when presented with an image of both a dog and a cat. CNNs contain 5 types of layers: input, convolution, pooling, fully connected, and output. This is the input layer that holds the raw pixel values of an image. The input, convolution, and pooling layers are where feature extraction is done. Think of the convolutional layer as a filter that passes over the image, scanning a few pixels at a time. The convolutional layer is the core building block of a CNN, and it is where the majority of computation occurs. It requires a few components, which are input data, a filter, and a feature map. It extracts different features from an image, such as the cheek, ears, nose, eyes, and then creates a feature map. When we talk about filters in convolutional neural networks, then we are talking about the weights. These are the feature detectors. These filters will determine which pixels or parts of the image the model will focus on. The filter is always smaller than input data, and the dot product is performed between input and filter array. Feature maps are what we get after a filter has passed through the pixel values of an input image. It is what the convolutional layer sees after passing the filters on the image. It is what we call a convolution operation in terms of deep learning. If we were to add numbers to the input map, the dot product, the multiplication of the input map and the convolution filter of the first scan, would look like the image shown here. If the full scan of the input would be done, you can see that the input would be reduced from a 5x5 table to a 3x3 table. The pooling layer takes small rectangular blocks from the convolutional layer and subsamples it to produce a single output from that block. There are several ways to do this pooling, such as taking the average of, or the maximum, or a learned linear combination of the neurons in the block. Essentially, pooling layers reduces the spatial size of the input, making it easier to process data. Pooling basically helps reduce the number of parameters and computations present in the network. Essentially, pooling layers reduces the spatial size of the input, making it easier to process data. Pooling basically helps reduce the number of parameters and computations present in the network. There are two main types of pooling: max pooling and average pooling. Shown here is max pooling, which takes the maximum value from each feature map, and average pooling, which takes the average value. Pooling layers are typically used after convolutional layers in order to reduce the size of the input before it is fed into a fully connected layer. The fully connected layer, or input layer, or the flattened layer, takes the output of the previous layers, flattens them, and turns them into a single vector that can be input to the next stage. A fully connected layer takes all neurons in the previous layer and connects it to every single neuron it has. Fully connected layers are typically used towards the end of a CNN, when the goal is to take the features learned by the previous layers and use them to make predictions. For example, if we were using a CNN to classify images of animals, the final fully connected layer might take the features learned by the previous layers and use them to classify an image as containing a dog, cat, bird, or duck. CNNs are often used for image recognition and classification tasks. For example, CNNs can be used to identify objects in an image or to classify an image as being a cat or a dog. CNNs can also be used for more complex tasks, such as generating descriptions of an image or identifying the points of interest in an image. CNNs can also be used for time series data, such as audio data or text data. What are recurrent neural networks? Let's begin by describing a few use cases. Our brains could easily process and understand the words that comprise the sentences that would comprise the language used in this book. But getting a machine to understand the text and language in this book is a complicated task. Similarly, translating text from different languages is also a very complicated task for machines. This is a picture of an audio wave. Our brains and ears can easily detect these sounds and understand what is being transmitted. Getting a machine to detect these sounds is a difficult task. These images show time series data. Think of time series data as time-stamped data. Has a sequence of data points in order based on time. Sequential data is unstructured data as compared to structured data. This image shows examples of both unstructured and structured data. The use cases just presented are an example of sequential data because the points in the dataset are dependent on the other points in the dataset, where the order matters. Sequential data includes text streams, audio clips, video clips, speech recognition, time series data, etc. Different data types need to be processed differently in order to train machine learning models. In an earlier video, you saw that convolutional neural networks are used primarily for image or voice data. And you learned that structured data, data in a table of rows and columns, can be fed into a multilayer perceptron and output predictions. But what do you do if you have qualitative sequential data with no predefined structure? And what if patterns in your data change with time? Earlier, we learned about the feed-forward neural network, but this type of network is not suitable for the use cases previously mentioned. Why is that? A feed-forward neural network allows information to flow only in the forward direction, from the input nodes through the hidden layers and to the output nodes. There are no cycles or loops in the network. Feed-forward networks cannot memorize previous inputs, cannot handle sequential data, and considers only the current input. To process data such as text, audio, and time series, a different network type is required. Where information about the past data needs to be kept in memory to predict the next word or sound or timestamp in the sequence. The word recur means to go or come back again, to happen again, and in this case of an RNN, to loop back onto the previous layer. Think of this as a hidden layer that remembers information through the passage of time. The idea behind an RNN is to train a network by passing the training data through it in a sequence, where each example is an ordered sequence. Once trained, new test data can be evaluated. For example, in order to determine the next letter in the word in the sequence shown in this training set, the previous word probability must be known. The word certification is a noun and is an entity of this sentence. And in these two examples, the word my precedes it. The probability that the letter C would follow the letter Y would be considered high. So, just like feed-forward and convolutional neural networks, recurrent neural networks utilize training data to learn. While traditional deep learning networks assume that inputs and outputs are independent of each other, the image shown on the left, the output of recurrent neural networks, depend on the prior elements within the sequence, the image shown on the right. There are 5 types of RNNs. The one-to-one is the simplest type of RNN, which allows a single input and a single output. It has fixed input and output sizes and acts as a traditional neural network. The one-to-many gives multiple outputs for a single input. It takes a fixed input size and gives a sequence of data outputs. An example is music generation. In music generation models, RNN models are used to generate a music piece with multiple outputs from a single musical note, which is a single input. The many-to-one RNN type is used when multiple inputs are required to give a single output. An example is sentiment analysis, where any sentence is classified as expressing the positive or negative sentiment. An example is a movie rating, where reviews are text as input to provide a rating. In the many-to-many equal type, the number of both the input and output units are the same. An example is machine translation, where the RNN reads any sentence in English and then outputs the sentence in French. In the many-to-many unequal type, the number of both the input and output units are not the same. An example is video classification, where every frame of the video should be labeled because they are not the same. Traditional neural networks have independent input and output layers, which make them inefficient when dealing with sequential data. Recurrent neural networks are used in sequence models because they have the power to remember what it has learned in the past and apply it in future predictions. This allows it to be used in applications like pattern detection, speech and voice recognition, natural language processing, time series prediction, image captioning, and language translation. You learn that feed-forward neural networks process data all at once. Convolutional neural networks require a number of steps to combine or pool information from distant parts of the input. You also learned about the sequential nature of RNNs, which refers to their ability to process data in a sequential order. And you learned that RNNs have a feedback loop that allows them to retain information from previous inputs, which is essential for processing sequential data. But what if your use case includes machine translation, text summarization, question answering? You probably can think of more. And you need to process the data as efficiently as possible. Well, the sequential nature of RNNs make it difficult to take advantage of modern fast computing devices such as tensor processing units and graphical processing units, which excel at parallel processing. A transformer architecture is a type of neural network well suited for machine translation, text summarization, and question answering tasks because they are parallelizable, which means that they are efficient to train. This means that they can be run on multiple processors or computers in parallel in order to speed up the training process. A transformer architecture is typically composed of an encoder and a decoder and uses the attention mechanism to learn relationships between different parts of a sequence. The encoder encodes the input sequence, produces a representation of it, then passes it to the decoder, which learns how to decode the representations for the relevant task. Essentially, the encoder learns the relationships between different words in the input sequence. The decoder takes this representation or learns the relationships between the input sequence and the output sequence and produces the output sequence. Transformer models can take a variety of data types, including text, images, audio, and time series. Transformer models are most commonly used for natural language processing tasks, again, such as machine translation, text summarization, and question answering. They can be trained on text data of any kind, including news articles, books, code, and social media posts. Transformer models can also be used for image processing tasks, such as image classification, object detection, and image segmentation. They can be trained on image data of any kind, including photographs, paintings, and medical images. Transformer models can also be used for audio processing tasks, such as speech recognition, speaker identification, and music generation. They can be trained on audio data of any kind, including music, speech, and environmental sounds. Transformer models can also be used for time series analysis tasks, such as forecasting, anomaly detection, and trend analysis. They can be trained on time series data of any kind, including financial data, weather data, and sensor data. This table summarizes the major comparisons between feed-forward neural networks, convolutional neural networks, recurrent neural networks, and transformer architecture networks. In this chapter, we focus on how to use the Keras library to build regression models. We'll build a simple neural network to reinforce the concepts you have learned. We'll start with an overview of the Keras Sequential API, one of the easiest ways to build, train, and evaluate a neural network. Then, we'll use an actual use case to implement the neural network using Keras. This will require loading and visualizing a dataset and then building the neural network. You'll then have a hands-on challenge lab with a solution that follows. The best way to understand neural networks is to build one for yourself. Let's get started with creating and training a neural network in Keras. By now, you should be very familiar with this multi-layer perceptron neural network. But how would you actually use this to solve a use case or problem? Would you believe that you can implement a simple neural network with just a few lines of code? Shown here is the same neural network but with code from the Keras Sequential Application Programming Interface, or API. Note that for each layer shown in the picture, there is a corresponding line of code. The input layer, hidden layer, and output layer each have a line of code. This is really all you need to build the model. There are a few additional steps, such as compiling and fitting the model, but these too are simple lines of code. Keras is perfect for those that do not have a strong background in deep learning because it is easy to learn. It builds the neural network using a modular approach with minimal code. You can design and iterate on machine learning ideas, moving from experiments to production very quickly. Keras consists of two objects, which means Keras is primarily built of two components, layers and models. Keras supports both recurrent and convolutional networks. Keras also provides support for training on central processing units, or CPUs, or graphics processing units, or GPUs. Keras offers a number of APIs you can use to define your neural network, including the Sequential API, which lets you create a model layer by layer for most problems. It's straightforward, just a simple list of layers and sequence. But it's limited to single input, single output stacks of layers. The functional API is a full-featured API that supports arbitrary model architectures. It's more flexible and complex than the sequential API. It is fully customizable, and it can accept multiple inputs and have multiple outputs. And there's also model subclassing, which lets you implement everything from scratch. And this is suitable for research and highly complex use cases, but really rarely used in practice. Using the sequential API, Keras simply arranges the neural network layers in a sequential order, which means the data flows from one layer to another layer in the given order until the data finally reaches the output layer. The simplest way to build a neural network is to use the Keras sequential API by using the add layer method, as shown here. To improve profits, organizations spend money advertising products and services. The channels they choose to advertise on can range from digital media to newspapers. One typical use case organizations encounter is how to optimally allocate budgets across marketing channels and measure the true contribution of each channel or campaign. They also need to predict or forecast sales given historical data from each channel or campaign. The dataset is composed of historical marketing channel data that can be leveraged to gain insights for spend allocation and to predict sales. The use case is a simple linear regression problem with just 5 variables. You have been asked to build this sales predictive model, and recall that neural networks are excellent for finding patterns in datasets. So for your simple neural network, you will build, train, and evaluate a prediction model for sales using the Keras sequential model. In this model, we feed the advertising budgets of digital, TV, newspaper, and radio to the model, and the model will predict sales. The advertising dataset captures the sales revenue generated from advertising in thousands of units for a particular product advertising budget in thousands of dollars for digital, TV, radio, and newspaper media. Using this data, you will be able to create a foundational marketing plan to discuss with your team. The dataset is based on data taken from an introduction to statistical learning with applications in R. However, for this course, the dataset has been updated to include a digital feature variable and modified to reflect the impact of this additional variable on sales. The number of markets has been increased from 200 to 1,200. Thus, the data consists of the advertising budgets for 4 media channels: digital, TV, radio, and newspapers, and the overall sales in 1,200 different markets. The goal is to produce a model that represents the best fit to some observed data according to an evaluation criterion. While Keras will do all of the heavy lifting for you, as a point of reference, the objective is to use multiple linear regression to assess the impact of advertisement on sales. Regression is a supervised machine learning process. It is similar to classification, but rather than predicting a label, you try to predict a continuous value. Linear regression defines the relationship between a target variable y and a set of predictive features x. Simply stated, if you need to predict a number, then use regression. We will evaluate the performance of the model using root mean squared error, or RMSE, a commonly used metric for regression problems. It is the loss parameter you will use for your Keras sequential model. RMSE is a metric that tells you the average distance between the predicted values from the model, the line on the graph, and the actual values in the dataset. The lower the RMSE, the better a given model is able to fit a dataset. No need to worry about learning the mathematics of this formula because you will not need to type it. Shown here is the Keras sequential model. Note here that for loss, MSE is shown. MSE is the mean squared error. We use this simple three-letter word to denote the loss, and we could use this. But root mean squared error is more popular than mean squared error, and we'll just take the square root of this once the model has run. Believe it or not, these 6 lines of code are all you need to build and train your model. Before you get to this point, you'll need to load the dataset, do a small bit of data processing, and then perform exploratory data analysis. These are the typical steps you would follow in any data science or machine learning project. The next videos walk you through the steps to help you on this journey of knowledge. In this video, we load and check the data, then perform exploratory data analysis. Here, we use a Jupyter Notebook to run our code. A Jupyter Notebook lets you run Python, an open source programming language. You'll find out more in the challenge instructions, where you'll only need to focus on building the neural network, which is writing 6 lines of code to train your network. So let's assume we've already imported the necessary libraries and modules in Python. The first step is to load the data. Here, the dataset is being pulled from the course's GitHub repo. Once the data is pulled in, you can check the first 10 lines. Note that the last column has the target that we would like to predict, which is sales. Shown here is the .info method, which gives you information on your dataset. The information contains the number of columns, column labels, column data types, memory usage, range index, and the number of cells in each column. Shown here is the describe method, which computes and displays summary statistics for the dataset. Shown here is the .shape method, which gives you the number of rows and columns in the dataset. Here, 1,200 rows, because the count starts at 0, and you also have 5 columns. Shown here is the .isNull method, which shows you any null values in the dataset. Shown here is a heat map, or correlation matrix. This visual shows how each feature is correlated to another. You would use this matrix to see how sales correlates with the other 4 features. Shown here is another heat map that clearly shows the top 2 features that have a relationship with sales, which is TV and radio. And again, just another way of seeing very quickly, using a gradient color scheme, how each media channel impacts sales. This is the same data in table form. Shown here are scatter plots that show the relationships between digital, TV, newspaper, and radio to sales. This slide shows how to split the dataset into the input features, which we call X, and the label, which we call Y. Shown here is the output of the normalization step. Use Keras preprocessing to scale the dataset so that all the X input features lie between 0 and 1 inclusive. This best practice is called normalization. Why? Essentially, if the inputs are not similar, it makes it difficult to initialize the neural network. You create potential problems for yourself if you feed into a neural network values that have widely different ranges. The network might be able to automatically adapt to these mixed data scales, but it would definitely make learning more difficult. Now, we are down to our last step in processing the data, which is to split our data set into a training set and a test set. We will use the code from scikit-learn called train_test_split, which, as the name suggests, splits our data into a training set and a test set. The code will store the split data into the first 4 variables on the left of the equal sign, as the variable names suggest. Unfortunately, this function only helps us split our dataset into 2. For our lab, we'll keep it simple and use the 2 sets. But as a best practice, you want to split the dataset into 3: training, validation, and test. As you can see, the training set has 719 data points, while the test set has 480 data points each. The X variables have 4 input features, while the Y variable only has 1 feature to predict. Since we will be using the Keras sequential model, we merely need to describe the layers in sequence. Model equal sequential means that we will store our model in the variable model and will describe it sequentially, layer by layer, in between the square brackets. Our first layer is a dense layer with 4 neurons and ReLU activation. Defining the input shape or the number of inputs is optional, so we did not add it. Recall that dense refers to a fully connected layer. The second layer is a dense hidden layer with 3 neurons and ReLU activation. Note that we do not have to describe the input shape since Keras can infer from the output of our first layer. The third layer is a dense output layer with 1 neuron, linear activation. And that's it. The model architecture is built. So now that we've built the model architecture, we need to configure the model by adding an optimization algorithm. Here we use ADAM. For the loss function, we use mean squared error. Configuring the model with these settings requires us to call the function model.compile. Training on the data is pretty straightforward and requires us to write 1 line of code. The function is called fit as we are fitting the parameters to the data. You have to specify what data you are training on, which is x_train and y_train. And then you specify what your validation data is so that the model can tell you how it is doing on the validation data at each point. This function will output a history, which you save under the variable history. You then specify the number of epochs or how many iterations you want the model to go through when training. And then for this simple network, we're just going to use 32. If you had a very large data set, you would want to specify a batch size. Once you run the code in this cell, the model starts training. You can now see that the model is training. What we might want to do is to plot the training loss and the validation loss over the number of epochs passed. In the first cell of the Jupyter Notebook, you may have noticed this code, which imports matplotlib that will help us create some really nice graphs of our results. Shown here is an example visualizing the training loss and the validation loss. The first two lines of the code says that we want to plot the loss and the validation loss. The third line specifies the title of this graph, model loss. The fourth and fifth line tells us what the y and x-axis should be labeled, respectively. The sixth line includes a legend of our graph, and the location of the legend will be in the upper right. And the seventh line shows the graph. Since the improvements in our model to the training set looks somewhat matched up with improvements to the validation set, it doesn't seem like overfitting is a huge problem in our model. Each curve shows that loss is decreasing through the iterations. To sum it up, you use matplotlib to visualize the training and validation loss over time to see if there's overfitting in our model. Overfitting is a common and serious problem because it affects the ability of our model to generalize on new unseen test data. Shown here is an image of an overfitting model. While the training curve is moving downward as loss decreases, the validation, our test data, is not. It is overfitting the unseen data. In this example, the model tries to fit the training data, even memorizing data patterns and any random fluctuations. Note here, the peaks and valleys are similar shapes. We cover ways to mitigate overfitting in our next chapter. After training, the model outputs a list of predicted values from the test set. You can print those test predictions, shown here on the left. You can also show the true value and the predicted value, shown here on the right. Notice that the two red boxes highlight the same numbers for the predicted values. You can also visualize the true and predicted values graphically, as shown here. Let's evaluate our model. First, note the code circled in red. Here, we take the square root of the mean squared error by using the numpy square root function. This is a fast and efficient way to calculate the square root of an array or a single value in Python. Recall that the square root of the mean squared error gives us the root mean squared error metric. Our model is achieving a stable performance with not much variance in the train and test set root mean squared error values, where we have 4.67 versus 4.72. In this challenge, let's build a simple neural network. Use the provided notebook in Google Colaboratory and run each cell one by one to see their output. Then, build the Keras sequential neural network we covered previously. Note, there will be a placeholder for you to add your 6 lines of code. Then, run the cell. Then, evaluate the model by entering the code to plot the graph. Run the cells and evaluate your loss curves. So, go ahead and give this a try. And when you're ready, join me in the next video to see the solution. You got this. Well, I hope you enjoyed that challenge. Let's now take a look at the solution. What we're going to do is just run through the cells one by one and see the output. So first, we need to import our necessary libraries. Then we need to grab our data from the GitHub repo, put that into a pandas data frame. And then we're using the pandas info function to get a concise summary of the data frame. And now we want to get some summary statistics of the data. And here we're just looking to see the shape of the data frame. And in this cell, we're really just using the isNull method to check and see if there are any null values. So let's do a little bit of exploratory data analysis. So here we're just going to plot the heat map so that the values are shown. And here we're going to use a correlation matrix. And then down here, we're going to have another correlation matrix, but this time in table form. We're going to here visualize the correlation using gradient coloring. And down here, we're going to use a scatter plot to again see the linear relationship between the features and sales. So now we enter the data pre-processing step. We're just going to go ahead and split the features X feature and Y target. We're going to go ahead and scale those features or normalize those features. Now we're going to split the data into a training and test set. I'm going to go ahead and print that and see what that looks like. So now we're at step 2, and this is the section where I challenged you to write your own code to create a simple 3-layer neural network. So your first line should have said model equals sequential because you're using the Keras sequential API. Then you needed to build the network by adding layers. So you added the input layer, you added a hidden layer, and you added an output layer. Your input layer had 4 neurons, your hidden layer had 3, and your output layer had 1. You then compile the model using the Atom Optimizer. You use MSE for your loss function and a metric as well. And then you fit the model by writing this bit of code. You should have put in 32 for your number of epochs. So let's go ahead and run it. It'll go through 32 iterations. And for our final step, let's look at a visualization of our model. So here we're using some standard graphing code just to plot the model and see the visualization. We're essentially plotting a graph of the model loss, where we are showing the graph of model loss in training and validation. You simply have to make sure that you have your metrics here and then just run the code. And there you have it. We have our graph, and you can see there's convergence. And this is just what we expected. I hope you enjoyed that challenge. Don't worry if your code doesn't look exactly like mine. That is the nature of working with data and its iterations. And if you're interested in learning more and playing more, check out the extras file we provided. In this chapter, we focus on understanding what makes a good model, which means you learn about underfitting and overfitting. Typically, the 2 major problems you will encounter with your models. You'll then learn the difference between model parameters and hyperparameters, which gives you the foundation to improve your model performance. You'll then work with the learning rate in a pre-coded lab to see how it impacts model performance. Models that are accurate and generalizable, which means you can feed unseen data into it and it will give you similar results from your validation results, are considered good models. Models that overfit or underfit are not. Also, good models have less minimal bias and variance errors. You will learn about bias and variance later in the chapter. In the previous chapter, you built a simple neural network using Keras. You saw how easy it was to build a 3-layer model, compile, and fit the model to the training data. You also learned how to plot the training and validation curves for the model loss, which gave you the loss curves shown on the right. So, how do you interpret this curve? Does it mean you have a good model, an underfitting model, or an overfitting model? Let's take a look at 3 typical examples that show loss curves for validation data and training data. The far left example shows an underfitting model loss curve. The middle shows a right-fitting model loss curve, and the right figure shows an overfitting model curve. Underfitting is a common problem in machine learning. An underfit model is a model that does not accurately predict the target variable, meaning that it is so simple it cannot create a relationship between the input and the output. It does not capture the relationship between the features and the target variable. Therefore, these models are unable to generalize. So think of an underfitting model as having poor performance on the training and the test data. The causes of underfitting occur because the model is too simple. The model is not trained long enough. The model is not regularized enough, or the model is not using enough data. Here are some of the solutions to underfitting. Make the model more complex by adding more neurons to hidden layers or adding more layers. Train the model for longer by increasing the number of epochs or iterations. Use more data, or use regularization, which you learn about later in the chapter. A good fitted model is a model that accurately predicts the target variable given the features. A good fitted model is neither underfit nor overfit. This means that the model has captured the relationship between the features and the target variable, but has not memorized the training data. We want to find the optimal fitting situation where the model has a similar gap between the training and validation error values. The model should be able to generalize to unseen data. Overfitting is a common problem in machine learning that occurs when a model learns the training data too well and is unable to generalize to new data. This can lead to poor performance on unseen data. An overfit model is a model that can accurately predict the target variable on the training data, but does not accurately predict the target variable on the test data. This is because the model is too complex and has memorized the training data. Solutions to overfitting include data augmentation, which involves artificially increasing the size of the training data by creating new data points that are similar to the existing data points. And this can help to prevent the model from learning the training data too well. Another solution includes regularization, which means you're adding constraints to the model to prevent it from becoming too complex. And you can also use early stopping, which involves stopping the training process early before the model has a chance to overfit the training data. In this video, we look at hyperparameters, which provides techniques to let you improve your model performance and avoid underfitting and overfitting models. If you are not using automated machine learning, where the training process is handled automatically by an AutoML framework, then hyperparameters need to be set by you. Lastly, model parameters are not hyperparameters. Let's look at some examples. This image shows a 6-layer deep neural network using the dataset features from our hands-on lab in the previous section. For example, digital, television, newspaper, and radio. Below the neural network, there is an expanded drawing of the summation and activation functions, which was covered in a previous video. Model parameters are something that a model learns on its own. They are estimated and learned by data during training. So when you think of model parameters, think of the model weights or nodes or bias in a neural network. These model weights cannot be manually set by you. They must be learned from the forward and backward pass workflow you saw in a previous video. But when you think of hyperparameters, think of what you can set. You can determine the number of epochs, the learning rate, and what regularization techniques to use. These are the components shown in the blue bubbles. There are other hyperparameters we'll cover later in the video. So let's look at this hands-on neural network from the Keras lab you previously built. Model parameters are learned during training when we optimize a loss function. Model hyperparameters cannot be learned during training, but are set beforehand. Model hyperparameters define the model's architecture, but are external to the model. Thus, they do not change with your model during training, and there is no learning as part of model training. Since they are not a part of the trained model, no values are saved. Hyperparameters are used to optimize the model performance. Typical hyperparameters for a neural network include the number and size of the hidden layers, nodes, weight initialization scheme, learning rate, activation and its decay, dropout, and gradient clipping thresholds, for example. Model parameters are estimated during the training with historical data. It is a part of the model. The estimated value is saved with the trained model. It does not define the model's architecture or optimize performance. As you may recall, the image on the left is of an underfitting model. In Chapter 4, you had a hands-on lab where you built a simple Keras neural network. The image on the right shows the model loss curves for the validation and training data for that model. The model loss curve appears to be very close to underfitting. You could tune the hyperparameters to improve your model's performance. And in this example, hyperparameters are knobs that you can tune or change to see if the model improves. You could change the model's architecture, the optimizer, the loss function, and the number of epochs. Shown here is the code you use to build your simple neural network in the hands-on lab. The code shows a 3-layer neural network with 4 input units in the first layer to receive the 4 features, a second hidden layer with 3 nodes or units, and 1 output layer. Note the optimizer as Adam and the metric or loss function you chose. Lastly, the number of iterations or epochs was 32. So, as you can see, hyperparameters are those which you supply to the model. The image on the left is the code for the simple neural network just shown. The image on the right shows the model's validation and training loss curves after training the model. This is the neural network that you will experiment with by manually changing hyperparameters. Here is an architectural view of that 3-layer network. The table presents 2 hyperparameter options you will first use to improve model performance. If you increase the number of layers, you can make this simple model a bit more complex. Increasing the number of nodes in the layers also makes the model a bit more complex and may help mitigate the underfitting. You can also adjust the learning rate, which is a tuning parameter in an optimization algorithm that determines the step size at each iteration while moving toward a minimum of a loss function. The image on the left shows the neural network with an additional hidden layer and an additional node. Note that the optimizer learning rate of 0.001 is the default learning rate for the Adam optimizer. It is shown here simply to show you that this learning rate appears to improve the model's loss curves, as is shown by the image on the right. So in addition to adding an additional layer and additional nodes, what if you increase the number of epochs? The loss curves now appear to underfit again. It appears that the most improved model is where the number of iterations is set to 32, as can be seen when the top image of the loss curves is compared against the good fit model image below. Typically, when training a model, the number of epochs is set to a large number, for example, 100, and an early stopping is used to determine when to stop training. This means that the model will continue to train until either the validation loss stops improving or the maximum number of epochs is reached. Now that you have seen an example of improving an underfitting model, let's look at how you can improve an overfitting model. The purpose of a neural network is to capture the dominant trends in the data. Overfitting is bad because it means that the machine learning algorithm did not capture the dominant trend in the data and therefore won't be able to recognize any trend on new data it has never seen. This means that the model did not really learn anything but only memorized the training data without understanding it. This means that your model cannot make accurate predictions. So your validation error is large while your training error is small, as is shown in the image on the left. Regularization is a hyperparameter technique to improve overfitting models. It refers to a set of different techniques that lower the complexity of a neural network model during training and thus may prevent overfitting. The image on the right shows a list of regularization techniques to help mitigate overfitting. Let's take a look at 3 of them: early stopping, dropout, and regularization. In early stopping, you stop the training process early, before the model learns the patterns and details of the data. Dropout works by randomly dropping out or setting to 0 neurons during training. Regularization is a technique used in machine learning to prevent models from overfitting the training data by adding a penalty to the model's loss function, which encourages the model to be simpler and less likely to overfit. Early stopping is a regularization technique that helps us avoid overfitting by stopping the training process of a neural network before it reaches the maximum number of iterations. The training process is stopped early before the model has had a chance to learn the specific details of the training data and start to overfit. So early stopping helps to avoid overfitting by monitoring, storing, and updating the best parameters during training so that when parameter updates no longer yield an improvement, after a set number of iterations, training is stopped and the last best parameter is used. If the performance of the model on the validation data set starts to degrade, e.g., loss begins to increase or accuracy begins to decrease, then the training process is stopped. To implement early stopping, you need to split your data into 3 sets: training, validation, and test. The training set is used to update the network parameters. The validation set is used to evaluate the network performance and decide when to stop the training. And this test set is used to measure the final accuracy of the network. The model is trained on the training set, and its performance is evaluated on the validation set. If the model's performance on the validation set starts to decrease, then training is stopped. Another approach to early stopping is to use a callback function. A callback function is a piece of code that is executed at regular intervals during the training process, which returns information from the training learning algorithm. As soon as your chosen metric stops improving for a fixed number of iterations, training stops, as shown in the image here, where the carrot's early stopping callback is used to monitor specific metrics like validation loss. Essentially, the callback function can be used to monitor the model's performance on the validation set and to stop training if the model's performance starts to decrease. With dropout, essentially at every iteration, a node is randomly selected and dropped, along with all of their incoming and outgoing connections, which means we don't use those nodes in both forward propagation and back propagation. This means that All nodes are not active at the same time, which forces the learning algorithm to spread out the weights and not focus on certain nodes. In machine learning, regularization penalizes the coefficients. In deep learning, it penalizes the weight matrices of the nodes. A penalty term is added to the loss function during training, which discourages the model from becoming too complex or having large parameter values. L1 regularization, also known as lasso regression, prevents models from overfitting the training data by shrinking the weight values to zero. This makes some features obsolete. This encourages the model to have fewer features with larger weights, which can help to prevent overfitting. The L1 formula on the right shows a regularization penalty term added to the model's loss function based on the absolute values of the model's parameters. L2 regularization is the most common type of all regularization techniques and is commonly known as weight decay or ridge regression. L2 combats overfitting by forcing weights to be small, but not making them exactly zero. The L2 formula on the right shows a penalty term added to the model's loss function, where it takes the square of the weights. For example, when you are predicting media sales, this means that less significant features for predicting media sales, such as newspaper budget, would still have some influence over the final prediction, though very small. The main goal of training a neural network is to acquire a model which is able to generalize optimally on new unseen data. Unfortunately, most neural network architectures often suffer from overfitting or underfitting. Recall that overfitting is the effect when the model fits the training data too well. That means the model is not able to make sense of unseen data it receives. Underfitting is a situation in which a model does not learn the underlying patterns of the data well enough. So, in addition to using hyperparameters, best practices for optimizing neural networks include many techniques that involve the feature dataset, from feature selection and feature engineering to normalizing, splitting, and shuffling the dataset. Recall that in the hands-on data pre-processing portion of the exercise to build a simple neural network, you normalize the features before using them in the model, since the features had different ranges. You also split the data into a training and test set. And it was noted that a best practice is to split the data into three: a training, validation, and test set.